Hi everyone, and welcome to Erik's Electronics Workbench. So I recently picked up this XL Microwave Model 3200 frequency counter. It has a very nice wide usable frequency range from 10 Hz to 20 GHz. Now this instrument was being sold as is, not tested for parts and repair. So with that sort of a description, I take that to mean that the frequency counter probably has some sort of an issue going on. Now in the listing, it was shown as being powered up, and I believe there was an input on the end connector, and the display did have some numbers being indicated. So I'm not sure if the instrument is just way off on its accuracy, or if there's some sort of another issue going on, but at least it does power up. So let's take a closer look. So one of the first things that I noticed about the frequency counter is that most of the screws are missing on the top and bottom covers. So there's a place for 40 screws total, 20 on the top cover and 20 on the bottom cover. So someone's definitely been into the instrument previously. I guess they got bored putting the screws back in place because there's only about 4 holding the top cover on and 4 or so holding the bottom cover in place. Now the reason that there's so many screws holding these covers on is because they want good RF shielding. So you don't want any gaps along the edges of the cover to the chassis, and you also want very good electrical connection everywhere around the perimeter of these covers because they need to act like a perfect RF shield. And again, if there was a gap in the corner or something like that, maybe just one screw here, you could end up with openings around the edges, and it wouldn't make a very good RF shield. So if I turn the instrument like this, you can see on the side how closely spaced and all along the edge right there, row of screws there, right there. This other side, it has another row right down here, and there on the bottom. And of course, when all those screws are in place, it's mechanically very strong as well. And also, I don't know if this can be seen on the camera, but this window for the LED display has a very, very fine mesh that's embedded inside that window, and it acts like an RF shield. So if you didn't have that mesh in there, this would just act like a big opening in the front panel, and you could have interference passing in and out. So the mesh is very fine, and it doesn't interfere with the viewing of the LED display, but again, it acts like an RF shield. So on the front panel, very typical of the controls and indicators you'd find on a frequency counter, so really nothing too exciting going on there. The BNC connector right here is for the low frequency input, 10 Hz to 120 megahertz. It is a 1 megohm input, so if you need a 50 ohm input, you'd have to use a 50 ohm adapter. And then the end connector is for the 120 megahertz to 20 gigahertz input. And this also has another feature. There's a power meter for the input that's on the end connector. So that's selected by this switch right here. And just take a quick look at the back panel right here. You can see line cord connection, fuse, GPIB connector, the address for the GPIB. These two BNC connectors right here, this one is the 10 megahertz reference oscillator output, and this is a reference oscillator input. It can be 1, 2, 5, or 10 megahertz. All right, so I'll take the covers off. Won't be too difficult, just a couple screws that are holding things in place, and we'll take a look inside and continue on. All right, covers are removed. And you can see on the inside of this cover, the other cover looks the same on the inside. There's this unpainted strip that goes all the way around the inside perimeter of the cover. That's keeping with the idea of a good RF shield design, so it makes good solid electrical contact from all areas around the inside of the cover to the chassis. So at the first glance, I'm not seeing any issues with the electronics. I don't see any components that look to be overheated. Nothing looks damaged or missing. So this board on the top is the digital circuitry. So you can see this is some GPIB interface over here, firmware in this chip, Zilog Z80 microprocessor. It looks very clean and looks to be in good condition, so nothing really stands out at the first glance. If I just turn the instrument over. So this is the bottom side of the instrument. You can see power supply back here. Board's labeled power supply right there. So this is a 60 Hertz transformer for the power right here, but there's also, it looks like some switching type power supply going on over here. This back panel is being used like a heat sink. There's some transistors and maybe some rectifiers that are bolted to it. And these transformers are much smaller, so that's what gives this away as a switching type power supply. Number of inductors as well. So under this shielded box right here is the interface for the reference oscillator in and out, back panel BNC connectors. Main oscillator board right here. And of course the RF circuitry under this shield. So the inputs up here on the front panel go right into this board. So yeah, it looks very clean. And I'm not, again, seeing any damaged components. Capacitors look to be fine. Now, if you're following along, you're definitely doing so at your own risk. An instrument like this is going to have AC line voltage coming in, so you need to use caution. Be aware of the dangers when working on AC line powered devices, so just take care and be safe. So I'll get this connected to my RF signal generator, and let's take a closer look and see how it's performing. So I spent some time going through the frequency counter's various functions. Now I see what the problem is, so let me show you what's going on. So the first thing that I checked is the internal time base, or the reference oscillator. It's supposed to be right at 10 megahertz, and it's very close to that value. It's not wildly out of spec. It's perfectly fine the way it is to do these initial tests, but it needs a little bit of a calibration, a little touch up, and I'll definitely do that. Now, I'm not going to cover that in this video because I've already shown that in another video where I do the calibration on a Hewlett-Packard 5334B frequency counter. So if you're interested in seeing how that time base is calibrated, definitely check out that other video. Just keep in mind that when you are doing calibration on an internal time base on a frequency counter, the external time base that you're using for that calibration needs to be extremely accurate and stable, because otherwise your calibration and your frequency counter is going to be all over the place. Also, when this internal time base is adjusted, the covers need to be installed. There's a little hole in the bottom cover. You reach through that, and the adjustment is on the circuit board right here. All right, so if I press this switch right here, just puts the counter in the standby mode. Then I'll turn it back on. So it does a normal display test. It says 10 megahertz, bus 1, and then normal display. So no problem with the startup. And now over here, I have my Rohde & Schwarz SME06 RF signal generator. And right now it's at 1 megahertz at plus 10 dBm output level. And on the end of the coax is this 50 ohm termination. It's just a feed through. So I'll connect that over here to the input right here. So that's the band 1, or the low band input. And remember, this is 1 mega ohm input, so I need to terminate it with this 50 ohm termination. So you can see it says 1 megahertz, very close to that value, just slightly off because, again, the time base is just a little bit off. That Rohde & Schwarz signal generator is very, very accurate on its output. So no problems there. That looks very good. So now what I'll do is reach over here and go frequency 120 megahertz. And we can see over here it says 120 megahertz. So no problems. That's the upper range of the low band input. If I change the resolution, step it up again, it takes a little bit of time. It has to count. It takes longer when the resolution is to its maximum. Give it a moment here. There you go. So no problems there. I can step the resolution down. I think it needs to calc. There it goes in. So I can set the resolution to whatever's needed. And I've gone through the other buttons on the front panel, work, no problems. The gate time works very well. No issues with any of that. So I'm not seeing any problem with the low band input. Seems to be perfectly fine. So now let me disconnect this. And what I'm going to do is take this adapter off. And I'll go over here and go frequency. Actually, you know what? I'm going to leave the frequency at 120 megahertz. That's perfectly fine the way it is. Just going to connect that over here and go to band 2. All right. So still 120 megahertz plus 10 dBm input, 120 megahertz being displayed. So it's selected on the band number 2 right there. So it is reading the frequency, no problem. And if I go over here to frequency, and I'll go all the way up to 6 gigahertz. And there you go, 6 gigahertz. And again, the resolution can be changed. I think that's the maximum. Nope, there it is. So no problem. I mean, that would appear to be working correctly on that input. Now, one of the other features this has is an RF power meter. So right here, it only works on the high band input. There's a switch right here, and if you press power meter, then it'll take that reading. So press that. And 6 gigahertz, and it says 4.6 dBm. Now you can see over here it's set to plus 10 dBm, and there's going to be some loss in this coax. This is, a coax that is suitable for 6 gigahertz. It's not the best choice, but it is perfectly acceptable. That's a lot of loss. Plus 10 dBm over there, 4.6 being read over here. I really doubt that there's that much loss in this coax. But now watch this. Go back down frequency, down to 120 megahertz. So now we have 120 megahertz being displayed, but look at the power level, minus 14 dBm. That's terrible. I mean, there's no way there's that much loss in this coax. Plus 10 dBm over there, minus 14 dBm over here. But think about what it's actually showing. As the frequency is going higher, it's indicating more and more power over here. That's just the opposite of what you would expect. The higher the frequency, the more loss in the coax. So you wouldn't normally see that this would go down, to more and more loss when the frequency is dropping down the way that it's indicating here. Well, that's a classic sign of an open circuit. So if you think about the input here, think about 2 wires that have opened up a little bit, okay, with a very small gap. If you have a DC voltage on this side, so 0 hertz essentially. And let's say you have 3 volts over here, and you take a measurement on this side and there's a break, no voltage, okay, nothing passes through. But let's say you have 6 gigahertz on this side and a very, very small gap. You will get a 6 gigahertz signal on the other side. Some attenuation, of course, but it will pass through because essentially that gap is acting like a capacitor. So the plates of the capacitor would be the conductor on each side, and the gap in the middle, the air, is the dielectric. So it's a classic sign that when you have an open circuit, the higher the frequency that you will get a signal going through, and the higher the frequency, the better the signal will pass. Because again, capacitors will pass an AC signal. So I believe the input on this has a problem and that there's an open circuit, and that's why we're getting this very unusual reading. I don't think the power meter is wildly out of spec on its calibration. Maybe it does need some calibration, but I think really the issue is an open circuit. Now here's something else that we can take a look at. And I played around with this a little bit here in this test setup, and I found that actually doing the frequency at 150 megahertz works a little bit better, just because of reflections that end up happening on the coax. So what I'm going to do, just turn this off for a second. Go like this. I'm going to put this T adapter. So this is just a simple T, the BNC connectors on each side. And connect that over here to the oscilloscope. Okay. And then the other side right here. That. And bring this over here to the frequency counter. Okay. So now it's coming from the RF signal generator through this T connector, so it taps off and we can see the displayed signal on the oscilloscope, and then it comes over here to the frequency counter's input. This is not ideal. Normally you should use a coupler in line like this, and then the coupler could tap off and it won't affect the impedance. A T connector like this is not the most ideal and can give reflections and other problems on the line. A coupler like this right here has a 50 ohm impedance on the input and then the output, and then the couple side right here on the center connector at the bottom right here, that would go off to the oscilloscope or the instrument you're taking the measurement, and it basically isolates this output from the input and the output. So normally this is what you'd want to use if you were trying to measure the signal and want to send it over to an oscilloscope. All right, so going back to this setup, if I go over here and I turn this back on, okay, so we have 150 megahertz plus 10 dBm output. You can see the displayed signal on the oscilloscope, okay, and the actual value and so forth isn't really important at this point. It's just that the fact that the signal is there and noticing where the peaks of that signal are. Now if I come over here and I disconnect this, so normally this is 50 ohm termination in here, 50 ohm impedance, but if I disconnect this, absolutely no change. Well, that's not good. It means that having this connected, well, of course we are getting a reading here, but it makes no difference when this is disconnected to the displayed signal over there. Now, this basically is just a 50 ohm dummy load termination right here, and then just this adapter. This is an SMA connector, and then this goes over to BNC. So now if I take this and connect it, check out the signal, it dropped. And that's what you would expect, because when this 50 ohm termination is placed on the end of this coax, it's loading down the output from the signal generator, and of course this is intended to operate into a 50 ohm load. It pulls the signal level down. When this is unloaded, the voltage, the output level will rise up. So again, if I take this off, it rises up. Really not ideal for the signal generator because it's just going into an open load right now. But if I plug this back on here, again, nothing. So this is not providing a 50 ohm termination. So definitely a problem going on here. And I think, I'll turn this carefully here. Cord is caught right there. There we go. I believe the problem is probably in this area of the circuit right here, because this comes right in. There's a very short, rigid section of coax that's in here, and then it disappears into this shielded area. So I need to disassemble this area and take a closer look, and let's see what's going on. And I suspect that maybe at some point this had too high of an RF signal that went in, and it may have damaged a component on the input. So let's find out exactly what the issue is, and I'll continue with the disassembly, and we'll see what's going on. So I removed this RF board, and I took the shield off the top of it. And to get this board out of the frequency counter, there's just 4 screws that hold it in place, but I had to remove the front panel as well. There's another 4 screws that hold the panel on, because these two connectors pass through the front panel, so it was really trapped in here, but by removing the front panel, then this board was able to just kind of lift up and out. There's a number of coax cables in the back, and this connector right here, just plug onto the back of the board, so straightforward to remove it. Now what I'm noticing is that on this board right here, this input, which is the input that's not working correctly, get this touched up for you here, you can see that a little bit better. So it goes right into this mixer module. You can see that rigid coax right there, and it goes directly in. So there's sort of a block right here is part of this module. This module plugs onto the board. It's a little bit hard to see from the side, but there's some pins. They go down to, it looks like a connector on the board. And on the other side of the board, you can see there's 4 screws right there. So need to remove that. And this module has the top cover is soldered in place, so I'm going to have to desolder that as well, see what's going on inside this module, because this rigid coax right here goes directly in, so I think the problem is going to be inside this module. I don't think it's on the board, below, but we'll see if there's any components underneath this module as well. Have a better idea when it's removed. All right, so I'll do that next. So I removed the 4 screws that held the mixer module onto this main circuit board. And with those screws removed, I was able to unplug the module right off the board. So there's a row of pins on the bottom of the module on this side and another row over here. They're gold plated. They look perfectly fine, nothing bent or damaged or anything like that. So the module just unplugs very easily. And then with the module out of there, I was able to desolder this top cover. See, there was 4 little areas of solder, and there's an RF absorbing material that's on the inside right there. You can see this strip right here. So with that top cover removed, I was able to take a look inside the module, and I didn't like my chances of being able to do a repair when I saw what was in there. Incredibly small components, just microscopic in size. I think some of the components are wire bonded in place, and others are traditionally soldered, but they're so small, and they're not marked on values, on many of them anyways. I don't have a schematic for this. It's a frequency counter, and I can't find a schematic or anything online. I found a manual. It has some theory of operation in it and some other information, but there's no schematics. So doing a repair inside this mixer module really didn't look like it was likely to happen. So I thought, well, it might be interesting to reassemble this and put a signal in here and trace through some of the circuitry and maybe find which component is faulty and not allowing the signal to pass through. At least, have an idea of where the problem is at, even if I can't fix it. So I put things back together the way you see it here. There's just 1 screw holding the board on. There's 1 screw holding the module in place. Wiring is reattached back here. I have a 150 megahertz signal being applied at minus 20 dBm from the signal generator. And look at the display. And of course, it's upside down, but it's minus 20.7. So there's 0.7 dB loss in the cable. Perfectly reasonable. And it works. Now, why it works, I don't know. But it is suddenly working again because this is an accurate reading. So what I'm going to do is I'm going to use my RF probe right here, and I'll use this probe to go into the circuit. Right here there's a trace on the input where the rigid coax goes through this block right here, and then it goes up to the first component. I'm not sure if it's a capacitor or a resistor, but I'll take a reading on this trace, which is essentially the same thing as taking a reading right in the coax and the line coming in right here. And you'll see on the spectrum analyzer, it's also reading minus 20 dBm. So really nothing to repair at this point. Why it suddenly works, I don't know. To be honest, I don't really trust it at this point. I don't know if it's going to keep working. So, that'll be, we'll find out if it's going to keep working or not, and we can revisit this if it suddenly stops working again. But yeah, for now, it is actually giving an accurate reading on the display. So let me move you over to the spectrum analyzer, and you can see what the reading is on this input trace right here. All right, so let's take a look at the spectrum analyzer. So I have the center frequency set to 150 megahertz, so you'll see a peak come up when I take the measurement, and the top reference line is set at 0 dBm, and then each division down is 10 dB, so the peak will be 2 divisions down, or minus 20 dBm, and then the marker is set on 150 megahertz, and you'll see the readout up here will also indicate minus 20 dBm. And again, the signal generator is outputting a minus 20 dBm signal, so that's what we expect to read, and the frequency counter is currently still showing minus 20 dBm, so it's reading correctly. Now this piece right here that's sort of out of focus is part of the active probe that I'm using. It's a Hewlett-Packard model 85024A, and again, here's the probe tip right there. The tip actually gets warm. There's active circuitry in the end right here. It's very high impedance input. It works very well. It's necessary when you're reading on RF circuits because you don't want to interfere with the circuit. You can't just probe in with a low impedance type probe. So this probe doesn't have an attenuator on the end right now, so it's just a 1-to-1 reading. So the reading that you see up here is exactly the reading that the probe is making. There's no attenuation factor. You have to be very careful with this probe because the damage level with no attenuation on the end is just a 1.5 volts peak. So very sensitive. Static electricity can also damage these probes. All right, so I'm going to clip the ground lead right here on this metal shield and go right over here to this trace right there. There you go. And there you go, right there. So minus 20 dBm, minus 20 and some change. We're very close to that value, so no problems. So the frequency counter's readout is correct right now. It is working the way that it's supposed to. So I had to remove the mixer module so that I could solder the cover back in place. So while the module is removed, you can see on the board where it fits right here, a little row of sockets there, another small row of sockets right there. And then on the other side of the module, you can see a row of pins there and right there. So those pins and sockets wouldn't be passing the very high frequency RF signals. Remember, this works up to 20 gigahertz. So the very high frequency comes in on this socket through this rigid coax, and then into this active circuitry that's right up in the top area. Definitely wouldn't be passing a 20 gigahertz signal through sockets and connections over here. So this circuit board has a shield on the other side. I removed that shield and looked at the solder connections just to make sure things looked okay, and they do. I don't see any problems. I also looked at the solder connection right on the other side of this rigid coax where it joins right here. I don't see any issue going on. And again, it is working now, so obviously it's hard to test for something that's defective when it's working correctly. But while this was installed on the board, I very gently pressed on the board and sort of flexed it around a little bit, and it's remained very stable. It didn't cut out or have any fluctuations in the readings. So I really don't know what the problem was. And the only thing that's really changed is the fact that it is unplugged from this board. So could it be that a signal between these connectors here and the module is somehow was not making a good connection? I really don't see how that could have been the case, given that it was affecting the RF signal and the impedance going in. Remember, it was not 50 ohms. And again, that wouldn't be affected by connections that are over in these sockets here. So really not clear exactly where the problem was, but again, it is working at this point. All right, the mixer module's cover is soldered exactly the way it was from the factory, and the module is attached to the circuit board. So time to get this all reassembled and test. All right, the XL Microwave 3200 frequency counter is completely reassembled, so let's see if it's still functioning correctly. So you can see it's displaying 120 megahertz, and I'm using the high band input. And over here on the signal generator, it's at 120 megahertz, 0 dBm. Now, I haven't calibrated the time base in here. I'll do that after the video is complete. So let's switch over to the power meter, because that's where the problem was before. So 120 megahertz and minus 1.1 dBm. So makes sense, being the frequency that's at the bottom end of this input, that's probably where it starts to drop off just a little bit anyways in its response. So not a concern. And earlier in the video, as you recall, 120 megahertz was way off on that value. So it looks perfectly fine, no problems there. Let's go up just a little bit. Let's say frequency 150 megahertz. We were using that value before. No problems with that, looks perfectly fine. Let's jump up, say frequency, say 500 megahertz. Yep, no problem there. And let's jump up to 1 gigahertz. Yeah, very reasonable. So just shy of a 1 dB of loss in the cable to be expected. Let's try, say, 2 gigahertz. Yeah, that makes sense. About a 1.6 dB. Slight loss in the cable, but not excessive. Very reasonable on that reading. Let's try 3 gigahertz. Yeah, makes sense. Looks good. Say 4 gigahertz. Yep, no problem there. 5 gigahertz. Starting to get a little bit more loss in the cable, but that's to be expected. The numbers look very reasonable. And this stops at 6 gigahertz, so we'll go to that. And there you go. No problem at all. So the frequency counter looks like it's functioning correctly now, and I really don't know what the actual problem was. I was never able to pinpoint a specific component or connection or something that was defective, but it does seem to work correctly now. So I'm going to go through the calibration on it and make sure that everything is spot on the way that it's supposed to be. I do have the calibration procedures in the manual I was able to find online. So I'll do that. If there's any other issues that come up during the calibration, or if the frequency counter stops functioning again, we can revisit this in a future video. But for now, it does seem to be functioning correctly. So I'm very happy with the result. It'll be a nice frequency counter to have on the workbench. So the repair part of this video wasn't all that interesting because there really wasn't anything to repair since it suddenly started working on its own, but nonetheless I hope you enjoyed looking at the frequency counter and some of the measurements that I made along the way. And if you did enjoy this video, please give it a thumbs up, and if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. So as always, thank you for watching, and until next time, take care, and goodbye for now.